Okay, welcome to all. Myself, Dr. Santosh Singh, working as Associate Professor in Department of Physics, Institute of Aeronautical Engineering, Hyderabad. Today, I am going to discuss about some optoelectronic behavior of some very popular semiconducting material like zinc oxide, titanium dioxide, and indium oxide. So that's why I choose the name of my today lecture, comparison of optoelectronic behavior of ZnO means zinc oxide, TiO2 means titanium dioxide, and indium oxide. Okay, so let's start the topic. So zinc oxide, titanium dioxide, indium oxide, and SnO2, one another member of same family. These are the metal complex oxide. SnO2 is known as a tin oxide, or the conventional transparent conducting oxide material, TCO. Transparent conducting means those who are conducting as well as transparent. Generally, both property will not found in a same or one material. Like if glass is transparent, but glass cannot be conductive. And if, let's suppose, iron is conductive or silver is conductive, so these metals are generally not found transparent. So if you are merge these two property, anyhow, these are known as TCO or transparent conducting oxide, are generally transparent conductors. But these transparent conductors are made with the help of oxide, metal oxide. That's why the another name came TCO, transparent conducting oxide. And these are very, very useful. These materials are very, very useful in optoelectronic application. Okay, that's why we choose ZnO, TiO2, indium oxide, and tin oxide. All are metal oxide. In between, among all these, indium oxide having some remarkable property regarding optoelectronic behavior. Why? Because once it will doped with tin, they will show some higher conductivity comparable to their metallic behavior or comparable to metals, and they also show some transparent behavior. So that's why whatever you are seeing the display devices in your modern day gadgets like cellular phones or any display devices where touch is applicable. So all the touch panels are made with the help of these such type of material. And the primary candidates is tin doped indium oxide, ITO, tin doped indium oxide, indium tin oxide. Okay. So these TCO are generally these TCO are N-type semiconductor because the ease of forming the oxygen vacancy, because oxygen vacancy can create easily, so that they can behave like a N-type semiconductor. Why? Because if oxygen vacancy is created, there becomes some charge imbalance. And what type of charge imbalance? Some negative charges will be exceed in number. Okay. Now doping element. So generally without dopes, suppose you are choosing only host material like ZnO, TiO2, indium oxide, SnO2. So generally their transparent or optoelectronic behavior is not that much level. But once you find out any suitable dopant, their optoelectronic behavior will enhance. So you have to find out what kind of suitable dopant you have to dope so that you can enhance the optoelectronic behavior. I am telling enhance. They already, as a host, they can also perform some optoelectronic performance. But if you choose some suitable dopant, their optoelectronic behavior may be enhanced or increased. So that's why all these materials are, as a host, their optoelectronic behavior, analyzing of optoelectronic behavior of all these material as a host is also very, very important. Okay. So I have chosen generally zinc oxide are found in 8 phases normally, but there are mainly 3 phases are well studied, and their name is Urjite B4 phase, B1 phase, B2 phase and B3 phase. B1, B2, B3, B4. So basically this B2 is high pressure phase and it will occur at around 254 or nearly 240 gigapascal. Once you reach up to that pressure point, your ambient condition phase, ambient condition means normal temperature and pressure condition phase, and that's name is B4, will convert into B2. So that's why I am not considering B2 phase. B1 is also some high pressure phase and its name is rock salt. But comparison to B2 phase, this B1 phase will occur at nearly 7 GPa. Once you applied the pressure over Woodgite B4 phase, that Woodgite zinc oxide symmetry will change into B1 rock salt phase. Okay, this B3 phase is also found in zinc oxide at ambient condition, means at normal pressure and temperature. But once you grow the zinc oxide layered structure over suitable substrate, then B3 type of structure will be grown. So that's why from this discussion you can clearly conclude that Woodgite B4 phase is actually the ambient condition phase. So it's optoelectronic behavior because this zinc oxide is a very promising candidate for optoelectronic performance. So their optoelectronic behavior should be analyzed by everyone, and you should also try to change some pressure and temperature conditions so that you are able to enhance the optoelectronic behavior of this ambient condition Woodgite B4 phase of zinc oxide. So generally people dope some dopant with zinc oxide, but what I did, I tried to change the pressure over the Woodgite B4 phase, but even not in positive direction, in negative direction. Means if you put the pressure in positive range of direction, the lattice will try to come near each other. Means the atoms will come closer to each other and their compact volume, means volume per unit cell, will decrease. But if you expand the unit cell volume, that kind of thing is considered as a negative pressure. So once you expand the unit cell, that is considered as a negative pressure. So what happened in that scenario? I try to find out in this research. So what happened once the negative pressure will apply over Woodgite B4 phase, this Woodgite B4 symmetry will convert into BeO type zinc oxide, barium oxide type of barium oxide. That barium oxide have their fixed geometry and shape and lattice position, lattice points where the atoms are situated. So this is the figure of Woodgite B4 phase, where these red atoms are showing the oxygen atom and these big atoms are showing the zinc oxide, and these big zinc oxide is surrounded by oxygen atoms in tetrahedral symmetry. This structure is known as tetrahedral. Okay, tetrahedral, octahedral is a kind of formation generally found in material science. So these zincs are, even if you see the entire picture, even oxygen is also surrounded by zinc and zinc is also surrounded by oxygen in tetrahedral symmetry, and these tetrahedron are corner sharing, means their corner are attached with each other. Okay, but here tetrahedral formation, once the zinc oxide converted into beta BeO phase, in negative pressure, C minus 4 GPa. It will convert to negative pressure. So what is this? This curve, this is the enthalpy versus pressure curve, and it can predict the transition pressure between two symmetries, okay, for same material, okay. So one symmetry is kind of B4, the another symmetry is BEO. So if you anyhow calculate the enthalpy versus pressure curve for this symmetry, so every symmetry have their own enthalpy, and once they will cut to each other, means both symmetry is now merged at particular pressure in same kind of similar kind of structure, okay. So these are the transition pressure point. This is the transition pressure point where the Woodzide B4 phase is converted into the BEO phase, actually beta BEO phase of zinc oxide, okay. So by this pictorial diagram, I am trying to show how the crystal structure change. So here you are able to see that zinc is surrounded by oxygen atom in tetrahedron formation, where all the tetrahedron are connected in corner sharing. Their corners are connected with each other. But in beta BEO forms, tetrahedral formation is not changed, but connection in between the tetrahedral is changed, and now they are edge sharing. Their edge are connected. Okay, see, okay, and also this B4 phase of zinc oxide is a kind of hexagonal phase, but this beta BEO phase is kind of trigonal or tetragonal phase, okay, tetragonal phase. Okay, now this curve is one famous scientist, Murnaghan. So Murnaghan gave their equation to draw the energy released by any phase once you change the volume of that phase and their energy, okay, energy released by that phase and corresponding volume. So they have put forward the relation between the corresponding volume of any phase and at that volume point what is the energy of that phase. So I also plot the energy versus volume curve for these two phases, and these two phases are also intersect here in higher volume region. What does it mean? Means volume is expanded, okay, and see the lowest possible energy is coming for Woodzide B4 phase. It predicts that Woodzide B4 phase is still a stable symmetry for zinc oxide, because those things who have a lowest volume is considered as a stable in material science or physics or any science. If you want to get stability, you have to lose your energy, okay, whatever your desires or energy, you have to left that thing, okay. Means once the system have in its lower energy, that system is always considered as a stable system. So in this energy versus volume curve of these two phases, the Woodzide B4 phase of zinc oxide has a lower energy comparison to beta BEO phase of zinc oxide. So you can say that this Woodzide B4 phase is still working as a most ambient condition phase or most stable phase of zinc oxide, okay. So this thing is clear. Even applying on the negative pressure, whatever your symmetry you are getting, that symmetry is not stable. Maybe that symmetry will show some remarkable optoelectronic behavior. So I will check the optoelectronic performance of Woodzide B4 phase, and zinc oxide phase, woodsite B4 phase and beta BeO phase, and we will compare the optoelectronic behavior of these two phases along with the other considered material like TiO2, titanium dioxide, and indium oxide. Okay, so in next part I consider the titanium dioxide, TiO2, and this titanium dioxide is also found in two different phases, namely rutile and enantiase. So this is your rutile phase, rutile, and this is your enantiase phase. So I have explored the optoelectronic behavior of these two phases, and this is your indium oxide. So see here, two types of indium are found for any single unit cell of indium oxide, and it is mentioned by indium 1 and indium 2. Based on their surrounding, this nomenclature indium 1 and indium 2 is given. So there are, in indium oxide, there are also several phase, Bixbyte, IA3, but most stable phase is IA3. It is already proven by several studies that IA3 is the most stable phase. That's why I have chosen IA3 phase of indium oxide. So I have already calculated their electronic behavior as well as optical properties of these phases and compared it. So what is that? This is the band structure, calculated band structure, EK diagram. Several lectures I devoted on EK diagram that now comes as a reality. This is the calculated figure. This calculation is done by me. So these are the calculated band structure for woodsite B4 phase, and this is band structure for beta BeO phase. So that lobe, this is what? This entire region is conduction band. Okay, this is the valence band. So the lowest part of conduction band and even nearly to some K points nearby gamma, this is the lowest point, occurs at the gamma K point. Gamma is the center of blue ozone. So this is the lowest point, conduction point, occurs at the center of blue ozone. Okay, and highest point of valence band also occurs at the same point, same K point, means center of the blue ozone. So you can see these are the direct band gap semiconductor material. So one thing is clear, ZnO is direct band gap semiconductor material. Here in beta BeO also we calculated the band structure and corresponding density of state. So this is the band structure plot BS. This is also BS, and this is the corresponding DOS, density of state. Okay. So I already discussed what is density of state, how the density of state vary once you go from bulk to their bulk to nano counterpart for same material. Okay. So what you have seen in the nearly same, the conduction band dispersion in both. Why I am using the word dispersion? Why? Because with the help of that dispersion, you can calculate the effective masses of holes and electrons. So with that dispersion of curve, dispersion, how much these are dispersive in nature, with that dispersion you can calculate. So if the curves are more dispersive, the effective masses corresponding to those particular curve will be lower. So your charge carrier will be moved faster in that direction. So your conductivity will increase. So I have calculated the effective masses of holes and electron for those material also. Okay. So this paper is published in MRX in 2016. Okay. Material Research Express, IOP publication, Bristol, London. Okay. Now, same thing I have to do for titanium dioxide. So band structure and corresponding density of state for rutile and TiO2. See here, rutile and TiO2, okay, band structure is coming, but there is no particular dispersion occur in the conduction band as well as valence band. So you can say whatever the conductivity will come in titanium dioxide, it should be low comparison to zinc oxide. So you can say in the regard of conducting, suppose you want more conducting material, more conducting optoelectronic material, and you have only two materials, zinc oxide and titanium dioxide. So what you have to choose? You have to choose the zinc oxide because your target is to achieve higher conductivity. So now this is the indium oxide, one of the best candidate in this family for optoelectronic behavior. So see their lobe and see their dispersion. So that's why it is best. It is best in regard of conductivity as well as transparency. Why? Because these curves are more dispersive. So corresponding effective mass value of holes and electrons will be very, very less. So it will be conduct very good. Okay. So now I will also calculate the optical behavior, optical properties of these materials. So this first figure is dielectric function, imaginary part of dielectric function of considered Woodzite B4 and beta BeO phase. And this is rest of the rutile and NRTS phase of titanium dioxide. This is the for indium oxide. Here two figure, many curves are there. So actually there are E perpendicular to C and E parallel to C. Okay, there are two axes. If the crystal is symmetry, they have centrosymmetry, there is no anisotropy. So both E parallel and E perpendicular with C is same. That is transverse component of electric field and longitudinal component of electric field. So once the crystal have a centrosymmetry, there is no any kind of anisotropy. So both is same. Otherwise, these two direction will show the different properties of imaginary part of the dielectric function. Epsilon is dielectric function. So epsilon 1 omega, actually epsilon is a function of frequency, is equal to I epsilon 2 omega. Okay, so this epsilon 2 is the imaginary part of the dielectric function and it is govern the entire optical behavior of any material. So I have plotted this dotted line is showing the E parallel to C and this solid line in every figure is showing E perpendicular to C. So I have considered E perpendicular to C for comparing with optoelectronic behavior of these phases with indium oxide. So what I have found, see here the calculated effective masses of charge carriers. Charge carriers means holes as well as electron in different direction. Direction means these in this direction, okay, or in this direction. What are the effective mass values? Gamma to Z direction, gamma to M direction, like that. So in different direction, I have calculated the calculated effective mass value for these material. And I also, on the basis of optical performance of these material, actually I am picking too much short for this topic because it is completely research. But around 1 month calculation is involved to getting all these results. Okay, so rutile TiO2, NRTS TiO2, then indium oxide, then two phases of zinc oxide. So see where is the lowest effective mass you are finding. So the lowest effective mass value is coming for 0.13, okay, among all the considered phase, in particular gamma to Y direction. Why? Gamma to, even gamma to Z direction also. Actually, this is maybe gamma to Y direction. This is effective mass of hole. This is the effective mass of electron. Gamma to Y, gamma to Z, 0.14 effective mass of hole. So why 0.14 is coming lowest value, and even effective mass of hole is also very less. Why such thing is happen? It is happened due to this sudden dip. See here, what I told, this curvature or dispersion is very, very important for calculation of effective mass of charge carrier. So a sudden dip occur here. See? So due to this dip, actually it should be like that to maintain the symmetry. But anyhow, due to the symmetry of the unit cell, this sudden dip occur in gamma to Z direction. This sudden dip in the band structure in negative side will increase the effective mass of, this is what, valence band. Okay, so in gamma to Z direction, the effective mass of holes, generally the effective mass of holes are heavier than electrons. But in this particular case, in this particular phase, you are getting the lower effective mass value of hole comparison to electrons, and even effective mass value of electron in this direction is also very, very less. See here, in gamma to Y 0.13 and in gamma to Z here 0.16, 0.14, gamma to Y, gamma to Z effective mass of electron, and in gamma to Y effective mass of hole is also very, very less comparison to effective mass of electron. So getting the lower effective mass value of both charge carrier is very good signature for getting the good optoelectronic behavior for any particular material. So I succeeded in my research for getting or exploring any well-established phase to their in negative expansion direction. Okay, and I got that very beautiful result where the effective mass value of hole and electrons are very, very less. Okay, so you can utilize this phase, this negative pressure phase of zinc oxide for optoelectronic candidate. But what is the challenge? The challenge is stability. How you can grow this phase. Okay. So, and I also calculated the transmittance. So see all the phases. This is Woodside before beta BEO phase, and I also compare with experiment of Woodside for experiment. So I got a higher transmittance value of beta BEO phase comparison to other phases. This phase is nearly similar to beta BEO phase. This is the indium oxide. This is the rutile transmittance. This is the NR-test transmittance. Okay. And transmittance is even calculated for parallel and perpendicular component of E. So in all the component, I have nearly same transmittance for beta BEO phase and indium oxide, but I got the very, very less effective mass value of charge carrier for indium, for beta BEO phase of zinc oxide comparison to indium oxide. So you can say in the conductivity regard, or if you want some higher conductivity, you can use beta BEO phase. But if you have any concern with transparency, you can go for well-established indium oxide phase. Okay, so that's all for my today discussion. So these are the conclusion what I already told. If you have a concern with conductivity, you can go for low density polymorph of zinc oxide, that is beta BEO phase. But if you want some higher transparency, with higher transparency with stability, you can use the well-established indium oxide. Okay, so that's all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.